Hello, everyone. Today we will continue discussing our topics in MOSFET switch. So, in the last class, we started together in this material, the multi-stage MOSFET circuit, and we discussed together the why do we need multi-stage MOSFETs, and we solved one complete numerical example, and we discussed everything in detail how to solve such uh, question. So today we will continue discussing the MOSFET topics. So the next topic is the FET switch or Jfet. So what is Jfet or PN Jfet? So basically, this is the configuration of the Jfet. You can see here this configuration. So the basic transistor action is the modulation of the channel conductance by the electric field perpendicular to the channel. So as you can firstly the construction, we have drain. So this is the drain metallic part. This is a source, metallic part, and the gate is connected here to these two P type materials. So we have like two gates now, and the channel will be conducting between these two P materials. So this is N channel 1, since this is N in the middle. So for the N channel Jfet, what do we have here? As we mentioned, we have two conducting parts, which are source and drain, and we have the gate in between. So the current flowing inside the channel itself between drain and source will be controlled by means of the electric field. So it's more or less similar to the concept of the MOSFET now, because the MOSFET also we have the field effect transistor. So we have here also field effect transistor. But we have junction FET. In MOSFET, we have metal oxide semiconductor. So oxide is a dielectric material. And since we had in MOSFET, we had dielectric materials, so it will make capacitance between the different terminals. Here we are missing this oxide material, so we don't have this dielectric material, and this means we will not have the similar capacitance shape that we have in MOSFET. So this is the difference between JFET and MOSFET. So MOS we have metal oxide semiconductor field effect transistor. So we have oxide material as a dielectric, but here we don't have this dielectric material. So it's gonna be now like two or conductance that will be controlled by means of the electric field. So the electric field applied where? Applied between gate and source. So between VGS or the voltage VGS will have a certain electric field. So this is S, this is G, and this is G as well. So between here and here, you will have a certain voltage drop or voltage difference. This voltage difference will control the electric field and at the same time control the conductance of this channel to flow the current between drain and source. And for sure, electrons are going to move from source to drain. So this means the current is moving from drain to source, opposite to the electron direction. Okay. So this is a concept of the N-channel Jfet. Sometimes we call it N-channel PN junction field effect transistor or PN Jfet, and most of the time we say Jfet. Okay, so we can by the end say we have N-channel Jfet and P-channel Jfet. So this is a shape of the N-channel Jfet. If we would like to compare now according to the construction, so this is the enhancement mode MOSFET. So this is MOSFET. And this is our J. FET. So as you can see here, guys, source is a metal, gate is a metal part, drain is a metal part as well, and here we have the oxide material. So you will have a capacitance between gate and source, capacitance between gate and drain, and capacitance between drain and source. So all of these are capacitances. Also, you have here, this is N and P. So you have here diode, and you have here another diode, correct? So this is connected internally in uh, the MOSFET. But here in the FET, we don't have the the oxide material, the dielectric material, so we are missing the capacitance. So there is no drain to source capacitance, or there is no drain to source the called the diode or the diode itself. So there is no diode in between the drain and source like what we have in case of MOSFET. So we call it body diode. Okay, so we don't have this body diode here in the Jfet. So this is just a quick comparison between Jfet and MOSFET. So regarding the concept of the operation now, it's very interesting since you have 0 volt applied between G and S. However, if you have drain volt, you will have a current flow, even if you have 0 voltage applied. So here we say for VGS equals 0 and small positive V drain to sources applied, and I mean it small because we are still in the first part of the operation. So we will call this part, like in MOSFET, this is going to be the linear mode. Okay. So this drain current is produced between the source and drain terminals, and the N channel acts essentially as a resistor. So in this case, guys, in the linear region, we will interact with the Jfet as a resistor. So I can say, for any resistance relation, you can say that resistance equals V divide R, V divide I. So R, for sure, this is the R between drain and source. It's equal to the volt between drain and source and the drain current. So this is a relation now. It's a very simple relation now compared to the MOSFET. You remember that in the MOSFET, we have 3 modes of operation. The linear mode of, relation was relatively complex even compared to the saturation one. But here, this is a linear mode relation. It's very straightforward. So it's nothing but a resistance. And by controlling the value of VGS, we will have different characteristics. So this is at VGS equals 0. Okay. So the relation is linear. So this is in the small values of V drain to source. So as you can see here, source is connected to ground. You have a positive small value of V drain to source. The gate terminal is connected to 0. So it's shorted, for instance, to the source terminal. So in this case, you will have a constant resistance for your channel, and the current will flow linearly with volt. So this is the first part of the operation. Now, assume that we applied more gate volt, but we will apply more negative gate volt, not more positive. So apply more negative gate volt, so it will be negative to the source. So if the source is 0, so VG is going to be negative sign. So for VGS equals negative volt, and small positive V drain to sources applied, still small because we are working in the linear region, the PN junction will be reverse biased. So you have here P, and this is already N. Since P is connected to negative and N is connected to 0, so this means the depletion region, this is the depletion region here, is going to increase. And increasing the depletion region means the current will decrease because, as you can see here, the channel width has been decreased. So reducing the channel width by means of increasing the depletion region, by means of apply more negative volt to the gate. So this will reduce our current. So we expect that the current will be reduced, for instance, like that, because as you can see, the width of the channel has been reduced, and you know that the relation between, for any conductor, resistance equals rho L divide A. So rho is the resistivity of the material, L is the length of the material, and A is the cross-section of the material. So since the A cross-section of the material, which is depending on the width of our channel, this A is decreasing, so we expect that the resistance will increase. And the increasing resistance means the current value will be decreased at the same voltage magnitude. So this makes sense to us. And the more negative again, the more depletion region and the less N channel until reaching to the minimum volt, which is the pinch off. So pinch off is like the turn off volt. So it's opposite to what we have now in the MOSFET. So for the MOSFET, we have V threshold, which is the minimum volt to turn on the MOSFET. But here we have pinch off volt, which is the volt required to turn off the Jfet. Yes, I mean it. The volt required to turn off. So this means this switch is normally on. It's not normally off like in MOSFET. So MOSFET is normally off, but Jfet is normally on. And the more gate voltage you apply, the less current until turning off your device. So if the volt reach to the value of V pinch off, the current will be 0. So this is equivalent to the cutoff region in the MOSFET. Okay, guys. So this is now the complete current travel at the different values of VGS at small drain to source values. So this is the linear region. Now, what are the difference now between Jfet and MOSFET according to our understanding? So the PN Jfet is a normally on. Normally on means with 0 applied volt to the gate to source, you can flow a current. So the channel can flow current once you have drain to source volt. So the device, so it's normally on device, that is, a voltage must be applied to the gate terminal to turn the device off. So it's the opposite to what we have in other switches like in MOSFET. So MOSFET, you need to apply a pulse or a voltage between gate to source in order to turn on. Here, we apply a certain volt in order to turn off. Okay, nice. So this is normally on device. Also, Jfet were developed before of MOSFET. So historically, Jfet has been designed and made firstly, but the applications and uses of MOSFET has far surpassed those of the Jfet in the market. But this is actually till a certain age. So this is according to the author in this textbook. However, nowadays, guys, due to the revolution in wide bandgap semiconductor switches, Jfet has started again, and we are using Jfet again in the market in a lot of applications. Okay, and I will show you some of the recent technologies of Jfet now in the market by the end of this class. One reason why we use MOSFET more than, or MOSFET has been spread more used than the FET in the last period, or in the last few decades. The reason is that the voltages applied to the gate and drain of the MOSFET are the same polarity. Same polarity means the positive value or negative value for VGS and VDS. So this is one reason in the opinions of the author, okay? Whereas the voltage applied to the gate and drain of MOSFET or of most Jfet have opposite polarities. I don't see this is a reasonable or a big deal, because by the end you will provide the pulses to the gate to source by means of another supply, not the same as the drain to source supply. This is in most of the cases. Okay, so I don't see that this is like a big deal why we don't use the JFET. And actually we are using JFET now a lot in industry, and even we do prefer using JFET in some applications compared to MOSFET nowadays, especially for the wide bandgap semiconductor switches like silicon carbide and gallium nitride. So since the revolution of the wide bandgap started, we started using again JFET a lot, because JFET has very small drain to source resistance compared to the MOSFET. So this is one reason why do we prefer using Jfet again in industry right now. Okay. Now, let's increase the voltage gradually, the drain to source volt, in order to jump to another region, not only the linear region of the Jfet. So, as the drain voltage increases, in positive value for sure, the gate to channel PN junction becomes reverse biased near the drain terminal. So once you have more positive value of drain, for sure, this is N channel here, and this is P channel here. So this means the depletion region here close to the drain will increase because it's more reverse. So let's say this is case number 1, where VGS was 0. This is case, sorry, all of cases VGS is 0. But here we have like a certain value of V drain to source. Second case, if we increase the drain to source more. So can you see here plus VDS, here plus VDS. So here, the second case here is greater than the first case. So as you can see, the channel is reduced here. So this is a channel width, and here the channel width is higher. Okay. And here more voltage, so the channel width has been decreased a lot, and here still channel width is high. So this means now, guys, we have nonlinear resistance. So the resistance will have like an E curve like that, and then it will be saturated. If you have very high depletion region here, it will be saturated. So this is a complete like travel of the Jfet from VDS equals small value until very high values. Okay, so this is a complete trip of the MOSFET, sorry, of the Jfet, starting firstly with small value of drain to source volts. So we are working in the linear region. Increase the drain to source volts, so the channel here will decrease because the depletion regions will be more wide compared to the previous case, because it's more reverse here. And the more voltage means more reverse PN junction for the depletion regions, and more wide depletion regions, and smaller width of the N channel until having very small value like that. So the current will be saturated, as you can see here in this figure. Okay, guys. So this is now a complete characteristic of a Jfet at VGS equals 0. Now, if we apply different values of VGS. So this is here the N channel Jfet. So this is a sample for sure of the N channel Jfet. So we don't have like two bars here because we don't have capacitance like in MOSFET. Okay, so just one plate, and this is a source terminal, this is a drain terminal, this is VDS, the current ID is flowing here, and this is G, and the VGS is here. So this is a sample of the N channel Jfet. And as you can see here, guys, here VGS equals 0. The more negative VGS, the less current, until having very small values here, which is VP, or the pinch off volt. Okay. So this is now the N-channel MOSFET, sorry, N-channel Jfet. What is the point of transformation from linear to saturation region? Still the drain to source saturation value. So what the drain to source saturation value? It's like the MOSFET. So it's VGS minus VP. And take care here, VP is a negative value. Okay. So this is now, guys, the N-channel Jfet. What about P-channel Jfet? It's completely the opposite. So this is a source terminal. This is a drain terminal. The current is flowing from the source to drain. And this is VS drain. And this is VGS. So G is here, S is here. So you can reverse the signs and say VSG. Okay, this is fine. If you would like to draw the characteristic, so this is the characteristic of VGS equals 0. But here, VGS is more positive, and the the pinch off volt is also here. What about the transition between linear and saturation region? Still the same value of V drain to source saturation, sorry, VSD this type in P channel. So this is a P channel Jfet. So it's going to be now VP minus VGS. Okay. So this is the P channel Jfet. What about the current and VDS relation, or the current voltage relation? It's very simple relation, guys. So we have, again, two regions, two relations. For the saturation relation here, so the relation is ID equals IDSS, which is the saturation current value, times 1 minus VGS over VP all square. So this is the relation in the saturation region. And what is the saturation condition again? The saturation condition is V drain to source is greater than V drain source saturation, which is VGS minus VP. Okay. What about the linear region? We mentioned that the linear region, it's completely a conducting resistance. So we can say RDS equals delta VDS divide delta IDS, or at a certain operating point. So it's going to be VDS divide ID. Sorry, not IDS, guys. We say it's ID. Let me please correct this typo here. Unfortunately, in the textbook, the relation of the linear is not there, but just to declare to you guys, it's simple relation. So he didn't mention this relation in the textbook because he considered it's like, since you know it's linear relation, it doesn't matter if he didn't mention the relation. But I do like to make everything clear to you, since in MOSFET, we discussed the different relations in linear mode and saturation mode. So I do prefer to have the same here also in the Jfet. Okay. So this is now, guys, the operation and characteristic of junction or PN junction FET. Let's start solving some questions. So in this example, guys, we need to calculate the drain current, the V drain to source saturation, in an N-channel Jfet. So assume the saturation current is 2 milliamperes. So the IDS is given, and the pinch-off voltage Vp equals minus 3.5 volt. So this is the turn-off volt. It's required to calculate I drain and V drain source saturation for VGS equals 0 for one time, VP over 4 for one time, and VP over 2 for another time. So 3 different values for VGS. Let's firstly, guys, start, since we need to calculate, guys, the drain to source saturation. So we need the transition point. So let's assume that the MOSFET work in the saturation region, because we don't have sufficient data to obtain the requirements from the linear region. So in the linear region, you have just one relation, which is V equals R times I. So we don't have VDS, we don't have ID, so we cannot get, because we don't have the value of R. So the only way to solve and get the value of ID and VDS here is to assume that it's working in the in the saturation region. Okay. So assuming that for the saturation region here, ID, you know, the relation ID equals IDSS, IDS saturation or steady state times 1 minus VGS over VP. So we have the current 2 milliampere, the saturation current, and 1 minus VGS different values, and VP is constant value here minus 3.5 volt, and this should be squared. So let's substitute now with the different values of VGS and calculate ID. So substituting with VGS equals 0, VP divide 4 and VP divide 2. So this means if you substitute firstly with 0, so 0, this means this term will be 0. So the current is going to be 2 milliampere. Okay. And this is making sense because if you draw the characteristic in the linear region, and then we have the saturation region. So the end of the linear region is the start of the saturation region. And if the saturation is 2 milliampere at VGS equals 0, so this means also the current will be the same. So this is the drain to source saturation, and this is already the saturation or V or the point of transition from linear to saturation region. So the drain to source is 2 milliampere. So this is ID, and this is here VDS. Okay. If VGS equals VP over 4, so this term now will be 4. So 1 minus 4 is minus 3. Minus 3 square is 9. Sorry, 1 over 4. So this is going to be quarter. Okay, so quarter square, so 1 minus quarter square, all square. So we will have now the value of 1.13. So we expect that the current is gonna decrease like that. Okay, at different value of VGS, which is here VP divide 4. So this is minus 3.5 divide 4 volt VGS. And then let's substitute at VP divide 2. So we will get a third curve at VP divide 2. So it should be higher. Sorry, not higher. It's lower. So this is minus 0.5 milliampere. So this is here for minus 3.5 divided 2 volt, and so on. So as you can see, guys, so this is the direction of VGS increasing. Okay, so this is the direction of VGS increasing until have VGS equals VP, so it will turn off. Okay, sorry, it will it will be completely turned off. Okay, which is VGS equal the pinch off volt. Okay, so these are the different values now of the currents we got. So we got 0.5 milliampere, we got 1.13 milliampere, and 2 milliamperes. Okay, so these are the different currents value we had for these three cases. Now we need to calculate the VDS saturation. So simply, guys, you know that VDS saturation equals VGS minus VP. So VGS in the different cases, we have it minus VP. It's constant. So we can calculate now first value is VGS equals 0. So minus VP, it would be 3.5 volt. So this value here is 3.5. For the second value, it would be 2.63. So the saturation here is for N is 2.63, and here will be less like that. So this is gonna be the transition or VDS saturation locus. Okay. So this is, guys, the different values we have in our case here. Okay. We have one comment here in the text box saying the current capability of the Jfet can be increased by increasing the value of IDSS. And what is the factor of increasing IDSS? Actually, it depends on the die itself, depends on the die of the material. So here, guys, you can see the current is 2 milliampere. I'm currently working with a Jfet in a certain application with a drain current reach in transient period for a duration of 100 microseconds reach to 2 kiloampere. So we have very large values of currents in Jfet, but this is in transient application in a certain specific application, but in steady state, the same switch can work up to 600 ampere. So still very high current compared to these small signal applications. So here in the book, the examples are more focused on the communication or small electronics applications. However, in industry, guys, you can find a lot of these devices working also in high power for power electronics. Okay, nice. So this is one example here, guys, to show you uh, the different values of VGS, how it will affect the performance of the Jfet. Now let's go to a design example. So design, again, guys, for the design means we need to control the DC analysis or the Q point of the transistor. So Q point again means we need to control the I drain and V drain to source. So this is the meaning of controlling that or making DC analysis. So we tune the value of the resistors in order to achieve a certain value for ID and VDS. What is the reason? So again, if we go back here, so the reason is we can operate the Jfet in the saturation region in some applications, like for instance, amplifiers. So it could work here. However, for linear mode, like what we mentioned in the MOSFET case, in case of like switches in power electronics or digital electronic circuit like logic gates, so we work only in the linear region. Okay, so biasing the switch or identifying the load line with the operating point of the transistor is nothing but the DC analysis we make and tuning the values of the resistors in order to force the transistor to work in a certain operating point. So this is what we need to do here now in this example. So this is a design question. He says, consider the circuit shown in figure with transistor parameters I drain to source equals 12 milliamperes. So he need to have 12 milliampere drain current. Sorry, drain to source saturation. So this is a factor given. And VP equals minus 3.5 volt, lambda assumed to be 0. So this is ideal case. Okay, so we don't have, no, we have. So we have the value of drain current, and we have the input resistance value. So the input resistance is nothing but, as we mentioned before, R1 and R2. So R1 plus R2 together equals 100 kilo ohm. But we don't have the value of each one. So we can just use this equation in our example to make the analysis. Design the circuit such that the DC drain current equals 5 milliamperes. So we have here the drain current. So this is ID. And the drain to source voltage is 5 volts. So we have 5 volt and we have the 5 milliampere. So this is now our operating point. Since this current is small and V drain to source is 5 volts, I can say by experience this is gonna be in the saturation region because the V drain to source is relatively high. And for sure, it depends on how much VG we are applying, but we don't know now the value of VG. So I can say we will start assuming that the Jfet is working in the saturation region. And based on that analysis, we can start tuning our circuit. So what is needed here, guys? We need to make a design. Make a design means find the value of RD, find the value of R1, R2, and RS. I assume he wrote the value here on RS in the solution, but RS is not given. Okay, so let's see, guys, what do we have here in the solution? So we need to make the analysis now of this circuit. So first step, guys, we will start assuming that, as we mentioned, the transistor is working in the saturation region. So starting firstly with the Jfet equation in the saturation region, I drain equals IDSS times 1 minus VGS divided VP. We don't have the value of VGS. VP is given, IDSS is given, and ID is given. So we can say now 5 milliampere equals 12 milliampere. Yeah, correct. 12 milliampere times 1 minus VGS divided minus 3.5, which is VP, all square. So from here, guys, we can get the value of VGS. So VGS is minus 1.24. So from the beginning, guys, if we compare the value of IDSS with the value of the drain current, you will figure out that this is not the final saturation current of this Jfet, which means VGS is not 0. Okay, so if VGS equals 0 in this case, so the drain current in the saturation has to be 12 milliampere. So since this is 5 milliampere, so this means VGS is not 0 here in this case. Okay, so from the beginning, we can figure out that VGS is not 0 in this case with V drain to source equals 5 volt. It could be in a linear region. It could be in the linear region. So I'm saying that, guys, let me draw that to let you like understand what I'm saying. So if this is a saturation, which is 12 milliampere, we have two different options. We can have the operating point in linear region and still the saturation current is 12, and here the current can be less. So here the current is 12 and here the current is 5. So this is fine. It's possible. However, here, this should be with very low value of V drain to source. And this is not the case because V drain to source is 5 volt. So V drain to source is relatively high. So this means, guys, we are not working at VGS equals 0. So most probably this will be another curve. Sorry. Another curve here at VGS equal negative value, not 0 value. And in this case, the current would be like that, for instance, 5 milliampere at V drain to source equals 6 volt. Okay, so this is my my preliminary expectation before solving the question. Okay, so now we already solved the question and we could get that VGS equals minus 1.24 volts. So this is the value of VGS. Now, for sure, you can check if your assumption was correct or not. So I can say here now, VDS saturation equals VGS minus VP. So this would be now minus 1.24 minus 3.5 volt. So this would be relatively small value, okay, which means it is let me calculate that, guys, in the calculator here. So this is minus 4.74 volt, and V drain to source is minus 6. Okay, so sorry, V drain to source is 6, and this is minus minus, guys. Sorry, this should be minus minus. So 1 minus 1.24 plus 3.5. So it's 2. 2.26 volt. So we have now VDS, which is 6 volt, greater than VDS saturation, which means we are working right in the saturation region. Okay, this is just to be sure that our assumption is correct. Next, we need to calculate the values. So now I got the value of VGS. So I got the value between this point and that point. I'm still missing all other parameters. I need to calculate everything. So let's start now from the circuit equation. Since we have the current here is 5 milliampere and the V drain to source is given, is it 5 or 6 volt? Let me check again, guys. Yeah, it's 5 volt. Sorry. So this is 5 volt. So V drain to source is 5 volt. Okay. And we need to get the values. So let's firstly, yeah, so RS is given, guys. RS is given 0.5 kilo ohm. Let's firstly use our source or drain current to get the value of Vs. So since I know the current here and I know the resistor, I know the voltage right here, so I can make a Kirchhoff now between this point and that point. So I can say Vs equals ID times Rs minus 5. if you apply Kirchhoff loop here from here to ground, so this volt here is -5, which means this is connected to a source, -5 to ground, so this is a supply, 5 volt. So from this point, Vs equals I drain times Rs minus 5. So this is the relation here. So Vs equals Id times Rs minus 5. So 5 milliampere times 0.5 kilo ohm minus 5 volts. So the Vs equals minus 2.5 volts. So we got the voltage of this point now. We got the volt or the potential of this point right here. And we know the value of VGS. So this means we can obtain the volt at this point, VG. So we can say, guys, VG equals VGS plus VS, because you know that VGS equals VG minus VS. So move VS to the left-hand side. So VG is VGS plus VS. So minus 1.24, which is VGS, minus 2.5, which is the value of Vs. So the value of Vg is going to be minus 3.74. So the volt of this point now, guys, is 3.74 volt. Now, we can apply Kirchhoff loop to get the values of R2 according to this branch. So how can we do that? So I can say the volt here equals, firstly, if this point is connected to ground, guys, so I can say the volt here is R2 divide R1 plus R2 times 5 volt. However, if this volt here is minus 5, so I can say now it is from the beginning. So it's R2 divide R1 plus R2 times the voltage here between this point and that point, which is 10 volt, minus 5 volt until reaching to ground. So this is a complete Kirchhoff now. And you know that in this example, it is given that R1 plus R2 equals 100K. So you can substitute here in this denominator now by the 100K. So you will have only one unknown in this equation, which is R2. So from here, guys, we can get the value of R2. So R2 equals 12.6 kilo ohm. Now, since we have R1 plus R2 equals 100K, so we can say R1 equals R2, 100K minus R2, which is 87.4 kilo ohm. This is for the first branch. So this is the input branch R1 and R2. We're still missing the value of RD. So we need to calculate the value of RD. How can we do that? We know the value here. We know the volt here. We know the current. We know the value of V drain to source. We know the value of Vs. So what about making a Kirchhoff here or a loop here to this branch? So we can say now 5 volt equals I drains times R drain, or let's say RD, plus VDS, which is 5 volt, plus Vs. And we know the value of Vs. Okay. So we know the potential of the point Vs. So we can stop here. If you would like to say, no, I would like to continue the circuit, so you can say instead of Vs, so you can say 5 volt equals RD plus RS times ID plus VDS minus 5. It's still possible. Okay, but since we already know the volt of this point here, so we can say 5 volt equals ID RD plus 5 volt, which is VDS minus, sorry, plus the value of Vs, which is minus 2.5 volt. So this is easier now, okay? So here in the textbook, he considered the complete Kirchhoff. So he said V drain to source equals 5 minus IDRD minus IDRS minus the value of V negative in the bottom, VSS, which is minus 5 volts. So we have only one unknown here, which is RD. so we can get the value of RD 0.5 kilo ohm. Okay, so this is the design problem. So in the design problem, we got the value of R drain, we got the value of R1, R2, which are the missing parameters in our circuit that will allow the Jfet to work at 5 milliampere and 5 volt feed drain to source. Okay, guys, so this is the DC analysis of this question. Okay, now we have some questions here. Let's answer these questions together. So true or false? Although MOSFET is more recent than JFET, it is preferred in today's applications. I would say, guys, so this question actually from the textbook, okay? Uh, I don't prefer such questions to be like uh, absolute questions because applications are changing time to time. So this textbook is not like very recent book. Okay, so I cannot say this is valid anymore because Jfet now is started to be used a lot in industry. So I cannot say we don't prefer Jfet now in industry. So I do prefer to say this is not applicable anymore. What is not applicable anymore? We don't prefer to use MOSFET than JFET anymore because JFET has some advantages compared to MOSFET, and we do prefer it now in today's applications as well. Okay, so according to the textbook, this question should be correct. Sorry, it's preferred. Yeah, MOSFET is preferred. Yeah, so according to the textbook, this should be true. Okay, however, today's application at the age of the book publication day, yeah, this would be correct. But today, in 2024, no, it's not correct anymore. Okay. And I will show you guys one of the recent uh, uh, manufacturer of the JFET and one of the recent switches used. It's not released in the market yet. It's still in preparation for production. Okay, and a lot of applications are requiring such JFET now in industry. Okay, another question here: the N-channel switches are preferred than the P-channel switches. So this is very general questions, guys. So N-channel switches are preferred more than P-channel. This is correct, and this is why, because we mentioned that the electrons speed is much higher than the channel sorry the hole speed, and this makes the drain to source resistance is much lower in case of the N channel compared to P channel. Okay, in MOSFETs or JFET or all of these applications. So yeah, this is right. The N channel switches are preferred than the P channel switches. Okay. Another question is why N-channel switches like JFET or MOSFET are preferred compared to the P-channel one? So this is another form of the question. So we already answered this question right now. Okay, guys. So this is what we need from this class, a summary. So in these slides, guys, we learned how to design the MOSFET multi-stage circuit, which we discussed this in the last class. So this is in the material, the summary of this material, these slides. The operation and construction of the PN junction FET, we discussed this today. Which switch is mostly used, P or N channel, we discussed this as well. Which switch is mostly used, MOSFET or PN junction FET, we discussed this as well. And now I would like to show you some of the most recent technologies of Jfet in the market. So let's see this together now, guys. So there is a company called Corvo. I'm working closely with this company and some of their products. So it's not released to the market yet. It is, as I mentioned to you guys, this is called Cascode technology. Yeah. Here it is. So this is called, guys, cascode technology. What the cascode technology? So in our class, we discussed something called multi-stages. So multi-stages can be like what we discussed in cascade, but this is called cascode. So what is cascode? Cascode is connecting the circuit or the switches in series like that. So here is our FET, Jfet, and this is made of silicon carbide. This can be connected in series with a MOSFET. So what is the benefit? The benefit is this Jfet is normally on. Normally on means at 0 gate pulse, it would be turned on. But this MOSFET or any MOSFET is normally off. So with small voltage MOSFET and large large volt silicon carbide Jfet, you can use this configuration together to make a normally off switch. So again, the benefit here is having a normally off switch, because in industry we need a lot to have normally off switch. So the Jfet itself is normally on. So we need to make it normally off. How can we make it normally off? You can connect a series device, and this series device is normally off. So since this is normally off, this is normally on. So by the end, since they are connected in series, it will be normally off. And when you turn off this MOSFET, the old branch will be off. When you turn on this MOSFET, it will keep this one on and conduct together. So this is the benefit of connecting such technology together. One other benefit is the gate to source resistance of this Jfet is very small. And if you use small avalanche MOSFET, so instead of using like 600 volt MOSFET, we can use just 40 volt MOSFET, because we don't need to have high blocking volt, because the Jfet can block the volt now. So if you need, for instance, a switch of 700 volt, you can use the 700 or 650 volt silicon carbide Jfet and only 50 volt MOSFET. So both of them together will be 700 volt, and it will work as a completely normally off switch, which is again required a lot in industry, the normally off one. So this is called cascode, or sometimes they call it combo. So we have Jfet and MOSFET in series connected together in a single package. Okay, so this is called cascode technology. I'm currently working on one like that in the market on toll package. So the toll package is not shown up here, but I can show you that in another data sheet. Let's see this one, for instance. Yeah, this is not the one I need. There's another. Okay, it's not here, guys, but the toll package sec fit. Yeah, so I'm working currently in a project with this switch. As you can see, it's 5.4 milliohms, 750 volt silicon carbide FET. Okay, so this one actually has cascode, and it's working in series with a MOSFET in just one package like that. Okay, so this package, by the end, we will have two gate terminals for the MOSFET and Jfet, and the other terminals here are for the source terminal. So we have many terminals for the source, and this terminal here is for the drain. So the source terminal of the Jfet is not given on the package, so it's internally connected. And we have by the end just the source of, let me show you again here. Yeah, so this is the company, it's called United Sec. Okay, but now Corvo has bought already this company, and this is the shape of this one. I would like to see the circuit again here to show you the circuit. Yeah, so as you can see, guys, this is the gate. Okay, so this is a gate terminal here. Okay, and this is the source terminal. So the source terminal is internally, it's not connected outside, but the gate terminal is connected outside. So this gate terminal, so it's a bit different actually to this shape. So the gate terminal is connected outside, and the gate of the MOSFET is also connected outside, and the source is available to the output. So it's not exactly like the one I'm using now in my work, but it had the same concept, which is having the cascade internal connection. Okay, and again, guys, this is preferred a lot now in industry. So according to our textbook, this was correct till like maybe a decade ago. Okay, but nowadays, no, we do prefer to use this JFET in a lot of applications. Okay, thank you so much, guys, and see you in the next class. Have a nice weekend.